The most powerful gamma-ray telescope in history has spent 15 years hunting objects smaller than an atom. Since 2008, the Fermi Space Telescope has scanned the sky, tracking every burst of high-energy radiation in our corner of the universe. After a decade and a half of non-stop observation, it hasn't found a single convincing candidate. If these objects are real, they would rewrite everything we know about the earliest moments after the cosmos was born. But if they don't exist, we lose an entire class of phenomena predicted by one of the greatest minds in physics history. And here's the unsettling question. What if the problem isn't with the objects themselves, but with how we're looking? To understand what Fermi was searching for, we need to rewind all the way back to the very beginning, literally, to the first fractions of a second after the Big Bang. In those moments, the universe was so hot and dense that energy wasn't spread out evenly. Tiny fluctuations appeared, minute, dense pockets where energy briefly surged beyond all limits. One theory suggests that some of these pockets became so extreme they collapsed in on themselves. Right there, in that primordial soup with no stars, no galaxies, nothing else. This is how primordial black holes could have formed, objects that didn't need a dying star to come into existence. And here, things get strange. Some of these hypothetical objects could be smaller than an atom, smaller than a proton, a point so tiny no microscope could ever see it. Yet this point carries a mass of tens of billions of tons. Imagine that, the weight of a mountain packed into a space an electron passes through effortlessly. Remember this detail, the mass of a mountain squeezed into the volume of an atom. It will come into play later. In the 1970s, Stephen Hawking showed that black holes aren't eternal. They slowly lose energy by emitting radiation. And the smaller the mass, the faster this process happens. Simply put, the tiniest primordial black holes should have evaporated long ago. But the bigger ones, with the mass of a sizable asteroid, could be dying right now. Their final moments would appear as brief but intense bursts of gamma radiation. That's exactly what the Fermi telescope has been searching for. 15 years, 0 results. Whether primordial black holes even exist remains a mystery. Sometimes, not finding something tells us as much as discovering it. Now, let's look at the other end of the spectrum. Black holes we actually know how to find. These don't form in the earliest moments of the universe, but in the final seconds of massive stars' lives. The process is tough, but straightforward. The star burns hydrogen, then helium, then heavier and heavier elements, until its core fills with iron. Iron is a dead end. You can't get energy from nuclear fusion with iron. The radiation pressure that held the star up for millions of years vanishes. The core collapses inward. If that core's mass exceeds 2 or 3 times the sun's mass, nothing can stop it from falling. A supernova explosion blasts the outer layers into space, leaving a black hole where the core once was. These objects typically weigh anywhere from a few to several dozen times the mass of our sun. You can't see them directly. Instead, we detect them by observing their effects on nearby stars, the X-ray glow of gas falling into them, and the gravitational signatures they leave behind. Estimates suggest there are tens of millions of these black holes scattered across our own Milky Way. Tens of millions of dead stars, transformed into gravitational traps, lurking between the spiral arms of our galaxy. Imagine the mass of a mountain compressed into a single atom on one end of the scale. On the other end, tens of millions of collapsed stars, each weighing several times the mass of our sun. We build our understanding somewhere between these extremes. But here's the catch. Our instruments are tuned either to catch gamma-ray bursts from subatomic ghosts or the X-ray echoes of stellar remains. What if there's something in between? Something our detectors simply can't pick up? Space-time is full of secrets, hiding things that neither gamma-rays nor X-rays can reveal. To find them, we need an entirely different kind of signal. This signal appeared in 2015. The LIGO Observatory detected gravitational waves, ripples in the very fabric of space-time, from the merger of 2 black holes. The energy, equal to 3 times the mass of our sun, didn't turn into light or heat. Instead, it warped the fabric of reality itself. The detector's mirrors shifted by a distance thousands of times smaller than a proton's diameter, and that tiny movement was enough to hear the universe in an entirely new way. General relativity had predicted these waves for a century. Now we could catch them using lasers. And here the real mystery begins. For decades, astrophysicists have been building a catalog of black holes. But in this catalog, a gap yawned wide. On one side, you have stellar mass objects, 5, 10, 30 times the mass of our sun. Dead stars collapsed into gravity wells. On the other side, supermassive giants sit at the centers of galaxies, millions, even billions of solar masses. But in between, nothing. Not a single black hole weighing hundreds or thousands of times the sun. It's as if nature skipped an entire floor in a building, jumping straight from the 1st to the 100th. Where did the middleweight class go? The answer didn't come from observations, but from the physics of the stars themselves. There's a mechanism that literally forbids certain stars from leaving behind a black hole. It's called pair instability. When the core of a supermassive star heats to extreme temperatures, photons inside start turning into particle-antiparticle pairs. The radiation pressure that holds the star up suddenly collapses. The core contracts. Nuclear reactions ignite with such force that the star doesn't just explode, it destroys itself completely. No neutron star remains, no black hole, just a cloud of gas scattering into space. Here lies a paradox. The more massive a star is within a certain range, the less likely it is to leave anything behind at all. Physics itself crosses intermediate black holes off the list of possible remnants. The catalog isn't just incomplete, it's incomplete by law. Here's the big question. If the laws of physics forbid the direct formation of such objects, do they even exist? On May 21, 2019, the LIGO and Virgo detectors picked up a signal that defied every known category. They labeled the event GW 190,521. 2 black holes, one with a mass of 85 times that of the Sun, the other 66, crashed and merged. 85 solar masses. That places it deep inside the forbidden zone of pair instability. According to theory, this object shouldn't exist. Yet, not only did it exist, it took part in the collision. The merger produced a black hole weighing 142 times the Sun's mass, the first confirmed intermediate mass black hole. About 8 suns worth of mass vanished, released as pure gravitational wave energy. 8 stars turned into a ripple in space in mere fractions of a second. But if binary instability prevents these objects from forming from single stars, where do they come from? One leading theory points to dense star clusters, regions where thousands, even tens of thousands of stars cram into a space just a few light years across. In this crowded environment, black holes don't just drift alone, they meet, they merge. The merger's product gains mass and finds the next partner, then another. Each collision pushes mass higher, climbing past the barrier nature sets for single stars. Not born, but assembled. Not breaking the rules, but finding a way around them. Here's what that means. Mathematics has shown that invisible giants of intermediate mass can grow by merging in the dark depth of dense clusters, a process that leaves no trace in X-rays or visible light, only ripples in the fabric of space-time. But if this middle layer really exists and fills up from the bottom, then at the very top, right at the centers of galaxies, we should find objects that break a whole different set of rules. And when we pointed our instruments there, those rules did indeed start to crack. The star S2 is one of the fastest in our galaxy. It orbits around a point where nothing can be seen. No light, no disk, no reflection, just empty space. Yet this emptiness propels S2 to speeds of 24 million kilometers per hour. To put that in perspective, that's about 2% of the speed of light. This star, heavier than our sun, races along its orbit as if thrown by an invisible hand. And it's not alone. Dozens of stars at the very center of the Milky Way trace loops around the same unseen point. Their paths are strokes on a black canvas, all pointing to a single object, Sagittarius A star, a supermassive black hole. 4 million times the mass of the Sun, packed into a region smaller than Mercury's orbit. Here's what's fascinating. Sagittarius A star is no exception. Supermassive black holes, with masses ranging from millions to billions of times our Sun, reside at the center of nearly every large galaxy. Nearly every single one. Not just some, not even most. Almost all. It's as if they're not just random visitors, but the very framework holding the galaxy together. In 2019, the Event Horizon Telescope Project, a network of radio telescopes stretching from Hawaii all the way to the South Pole, achieved something once thought impossible. It captured the first ever image of a black hole's shadow. Not our own black hole, but the one sitting at the heart of galaxy Messier 87, 55 million light-years from Earth. The photo shows a blurry orange ring surrounding a dark void. That's the shadow, the region where light simply won't return. This black hole holds 6.5 billion times the mass of our Sun, yet all that appears in the picture is the pitch black center. But behind that darkness lay a connection astrophysicists had suspected for a long time. The mass of a supermassive black hole closely matches the mass of the galactic bulge, the thickened core at the center of its galaxy. The bigger the black hole, the more massive the galaxy's core. They grow together, not side by side, but linked, like two living organisms feeding each other. Which one comes first? That question remains unanswered. Yet, the very existence of this correlation tells us something powerful. The black hole doesn't just live inside the galaxy, it plays an active role in building it. Now, let's leap back 10 billion years. Quasar Ton 618. Its light has traveled over 10 billion years to reach us. We see it as it was when the universe was less than 4 billion years old. At the heart of this quasar lies a black hole weighing up to 40 billion times the mass of the Sun. 40 billion. That's 10,000 times heavier than the black hole at the center of our galaxy, Sagittarius A star. The accretion disk swirling around it radiates energy that outshines the Sun by hundreds of trillions of times. If black hole M87 is silence, where not even a photon escapes, then Ton 618 is a roar. Its hot plasma, twisted into a funnel, shines brighter than an entire galaxy. Brighter than a trillion stars compressed into a single point. And here's where the real problem begins. It's not that such an object exists, it's when it exists. The universe is less than 4 billion years old, yet this black hole has already amassed 40 billion times the mass of our Sun. Physics sets a strict speed limit on how fast matter can fall in, known as the Eddington limit. It's the point where radiation pressure from the infalling material pushes back against new matter, like a vacuum cleaner on full blast suddenly blowing dust away instead of sucking it in. Calculations show that, under normal conditions limited by this threshold, growing a monster that massive in the given time is simply impossible. There just aren't enough billions of years. John Wheeler, the physicist who actually coined the term black hole, once said, "Black holes have no hair." He was referring to their striking simplicity: mass, charge, spin, and nothing more. But just because their description is simple doesn't mean their origins are. To explain the existence of these early cosmic giants, physicists propose ideas that break the usual rulebook. Instead of slowly gobbling up stars one by one, these black holes might have formed from the direct collapse of massive gas clouds, collapsing all at once, skipping the star stage entirely. Another possibility involves super Eddington accretion, where matter falls in so densely and rapidly that radiation can't push it away fast enough. Both scenarios demand conditions that could only exist in the early universe, and to this day, both remain hypotheses. It paints a strange picture. These objects devour everything around them, yet they also shape the very galaxies they inhabit, destroyers that define cosmic architecture. And the farther back we look, the larger they become, as if the earliest ones didn't grow gradually, but appeared fully formed. But even 40 billion times the mass of our Sun might not be the limit. Some theoretical models suggest that an object's mass can become so enormous, its average density drops below that of air. These hypothetical monsters even have a name. Physicists call them slabs, staggeringly massive black holes. Each one packs a mass exceeding 100 billion times that of our Sun. That's heavier than our entire Milky Way, every star, planet, gas cloud, and all the dark matter combined. Not a single slab has been found yet. No observations, no indirect clues. Pure math, born from equations rather than telescopes. But if even one of these giants lurked beyond the observable horizon, its presence would reveal itself through gravity so intense it wouldn't just pull in stars or galaxies, it would draw in entire clusters of galaxies, hundreds, even thousands of galaxies, obediently drifting toward an unseen center of mass. Hundreds, even thousands of galaxies, like debris slowly swirling down a bathtub drain. And this is where the truly strange story begins. For decades, we've watched galaxy clusters behave in ways that just don't add up. Something unseen pulls on them, something that doesn't show up in any image or spectrogram. We called it dark matter, admitting honestly that we have no clue what it really is. In some theoretical models, slabs come up as a possible explanation for at least part of this mystery. The logic is straightforward. A black hole the size of a galaxy is, by definition, invisible. No light escapes from it. Yet it exerts a gravitational pull on everything nearby, the perfect candidate for the invisible architect. But this elegant theory faces a tough challenge. The cosmic microwave background, the ancient light left over from the first 100,000 years after the Big Bang, acts like a snapshot of the young universe. Every massive gravitational object leaves its mark on this snapshot, subtly warping the background temperature. If there were many of these slabs, their traces would stand out on the cosmic microwave background map as clearly as fingerprints on glass. Yet, the data from these maps show no such patterns. That means, even if such objects do exist somewhere, they are few and far between. Still, even a handful of them is enough to shake up our usual understanding. The main surprise about these slabs isn't their mass or their gravity. It's what happens to their density. When you hear the term black hole, your mind instantly pictures a point of absolute compression, where matter is squeezed beyond anything you can imagine. Like a teaspoon that weighs billions of tons. For small black holes, those tiny objects about the size of an atomic nucleus, which we mentioned earlier, that image is spot on. Their density surpasses anything found in nature. But the Schwarzschild radius formula works both ways. The average density of a black hole equals its mass divided by the volume of the sphere inside its event horizon. Mass increases linearly with the radius, but volume grows with the radius cubed. In other words, as a black hole grows, its internal space expands far faster than its mass does, and so its average density inevitably drops. For a black hole with a mass of several billion suns, the average density ends up comparable to that of water. Ordinary water, the kind that flows from your kitchen faucet. And for objects even more massive, like hypothetical slabs with hundreds of billions of solar masses, the density drops even further, down to the density of air. Wait, read that again. A black hole, a place where not even light can escape, can be less dense than the air in the room you're in right now. Inside the event horizon of such a giant, there's no wall of compressed matter, no monstrous pressure. It's spacious, almost empty by cosmic standards. And if someone crossed that horizon, they probably wouldn't feel a thing. No sudden jerk, no crushing squeeze, just a quiet, subtle crossing, and suddenly you're inside. What we usually think of as the defining trait of a black hole, its deadly crushing density, turns out not to apply to all black holes. It's a trait unique to the small ones. Scale flips the nature of these objects completely. That lethal trap, as the size grows, transforms into a sparse void, indistinguishable from ordinary space. This idea that a massive gravitational funnel might be as empty as the space around us leads to a question mathematicians approach with great caution. Because when you plug in not the mass of a galaxy, but a much larger mass, the scale of the entire observable universe, the numbers start matching up with an unsettling precision. The mass of the observable universe is around 10 to the 53rd power kilograms. It's a number so vast, it's almost unfathomable. But you can plug it into a formula. The very formula Carl Schwarzschild derived on a scrap of paper in the trenches of the First World War. Multiply 2 by the mass, then by the gravitational constant, and divide by the speed of light squared. The result gives you the radius of the event horizon for an object of that mass. That radius comes out to roughly 4.5 times 10 to the 26th meters, more than 46 billion light years. The radius of the observable universe measures about 46.6 billion light years. The match in order of magnitude is almost perfect. It's like measuring the length of a room's wall, then calculating that same length using a completely different formula, and ending up with the exact same number. But that's not all. The average density of a hypothetical black hole with the mass of our entire universe comes out to about 10 to the minus 29th grams per cubic centimeter. The current average density of the universe, measured through cosmic microwave background radiation and the distribution of galaxies, falls right within that same range. Simply put, both the size and density of our universe match what you would expect inside a black hole of this scale. Two coincidences don't prove anything, but they stop feeling accidental when you uncover a deeper structural symmetry behind them. The equations of general relativity describe gravitational collapse, the way matter falls inward, using a specific geometry of spacetime. And this geometry isn't just metaphorically similar to the metric of an expanding universe. It matches at the level of tensors and field equations. Collapse and expansion are two perspectives of the same curvature. It's as if the Big Bang and the formation of a black hole were the same event, only observed from opposite sides of the horizon. Some mathematical models suggest that our universe might form inside a black hole, embedded within a higher dimensional parent space. Not just 3 dimensions plus time, but 5, 6, or maybe even more. In this view, our 3-dimensional world acts like a membrane, nested within a structure we can neither see nor measure. Yet, and this is crucial, all of this remains purely speculative. It's not part of the standard cosmological model. It's not an established fact. Instead, it sits at the cutting edge of theoretical physics, where equations race far ahead of observations, perhaps forever. We don't know if our universe is the interior of a gravitational collapse, and maybe we never will. The event horizon, if it exists, is opaque in both directions. But let's imagine for a moment that it's true. Imagine a headline tomorrow morning presenting undeniable proof. We live inside a black hole, embedded within a larger space we can never reach. What changes? Your morning coffee will still taste just as bitter. Kids will still go to school. The sunset over the ocean will remain a sunset. Nothing that makes up the fabric of human life will shift even an inch. And maybe that's the strangest part. The scale of the answer doesn't match the scale of its consequences. The universe could be a closed sphere with no way out, yet everything that truly matters still fits within arm's reach. Poor Schwarzschild. He wrote his equations by kerosene lamplight, dying of illness in a trench on the Eastern Front. He had no way of knowing that his formula would one day describe not just the edge of a star, but the boundary of all existence. And yet, right now, as the screen glows and this voice reaches you, telescopes keep collecting photons arriving from the edge of the observable universe. Each photon carries clues about the curvature of space it has traveled through for billions of years. Whatever the answer turns out to be, it will change everything. If we are inside this boundary, it reveals something about the nature of reality beyond our current understanding. If we are not, the very fact that the universe's size matches this radius still demands an explanation we simply don't have. In either case, we stand at a threshold, and that threshold lies within us.